the support of F should be some curved class beta. In the Euler characteristic of F, we also fix be some integer, n. So when we look at this moduli problem, we have to add one stability condition. That condition is that the co-kernel of S is zero-dimensional. So pure sheaf here, this means pure of dimension 1, meaning that every non-zero subsheaf of it also has support of dimension 1, supported on a curve given by beta. So if we put all these conditions together, we get moduli space, which is usually denoted Pn of x beta, space of stable pairs. So you should think of this as being very closely related to the moduli space of ideal sheaves appearing in Donaldson-Thomas theory. This stable pair space, the Donaldson-Thomas theory, and Gromov-Witten theory all have correspondences between them, which are some combination of conjectural and not even completely stated yet. But like those other moduli spaces, the moduli space Sable pairs, developed by Pandharipande and Thomas, has a perfect obstruction theory. It gives you a nice virtual class. So and the virtual dimension is the same virtual dimension that appears in these other theories. That is, against our curve class, we integrate the first string class of x. Okay, so if x were Claubiel, then this would be 0, so we would actually be able to immediately start getting numbers out of it. But in general, this isn't going to be the case. So this is where the descendants come in. So I'm not going to go into the details of how one defines the descendants, but should be viewed as analogous to descent in Gromov-Witten theory or Donaldson-Thomas theory, very similar to descent in Donaldson-Thomas theory, of course. So these descendants, they're defined using the universal sheaf that you have. On x cross p on x beta. Basically, you're just descendants are a way of homology operation that twists what you have by trig characters of this universal sheaf. And you also take cohomology classes on x. That's what this gamma is. So by using the descendants, you can hit the virtual class with them, shift around dimensions to actually get down to a situation where you can count something to get actual stable pairs invariants.
Sorry, so this descendant
Yeah, you actually use the I plus second Chern character is how the normalization works. Okay, so once you have descendants, you apply them to your virtual class. You then count the number of points you get after you bring things to degree 0. And so the descendant invariance we have was, it was saying we take some number of these descendant operations I haven't defined and apply them to the virtual cycle. And then see how many points we're getting, integrating 1 on it. And now our dimension formula, there's one parameter we had here, n, which it didn't depend on. So that's nice. It gives us something to sum over to get a generating function. So I'm summing over all integers n and z, but it's not too difficult to convince yourself that for n sufficiently negative, these moduli in fixed x and beta, this moduli space will be empty. So really, you are getting a Laurent series here. Coefficients are rational. You've lost integrality because of how the descendants are defined with some Chern character. So this is the descendant partition function. Notation for it, zx beta of the descendant insertion so a priori this is just a Laurent series, but the most basic conjecture about it is first made by Pandharipande and Thomas. Is that this is actually the Laurent series expansion of a rational function in Q. I'm just going to write like that. So this is known in some cases, but not in most. It's known, for instance, for Claude Lx, and well, then you have no insertions. Yeah, it's known for Claude Lx.
What about toric?
Yeah, so toric, I'm going to be talking about here is the sort of main component in recent theorem, saying that not only is this true for toric with arbitrary descendants, but it's true equivariantly. That is, you can carry out this whole construction in equivariant cohomology using your torus action. I'm going to put the T here to denote the torus action. And in the end, you get a rational function of Q and your 3 equivariant parameters. 3 since you're in threefold. So this is stronger than this statement for toric varieties. You can always recover the non-equivariant state by taking non-equivariant limit. So, but I believe that these are the only 2 cases where it is currently known for Claude X and no insertion, actually primary insertions only, I think, and for arbitrary insertions for toric X. So I'll be talking about the key ingredient of proof of this theorem. Yes.
What happens here at tau 0, 1? So I was like something like a string equation. Do you have an obvious equation?
No, it's 1, but it has this insertion in from the virtual class.
I think you. I think the answer to your question is that, yeah, there are analogs of like string equations, et cetera, but usually, sort of the history of this theorem is that it was first proven in a toric setting for primary insertions only, just tau 0 of something, by using the correspondences that were proven between all of these theories, between Sable pairs and Donaldson-Thomas and Gromov-Witten. All of those correspondences are fully proven in the setting where you are toric and you have only primary insertions. So in those settings, this rationality statement followed from the rationality statement that was previously known in Gromov-Witten theory. So the new content in this theorem is extending that via completely different methods to arbitrary descendants. Okay, so how does one go about this? Well, you want to use the torus, which means that you are going to be using equivariant localization. So localization, as usual, means that you can write everything as a sum of contributions from fixed points, torus fixed points. So what do these torus fixed points look like in the case of Sable pairs? Well, as usual, if you have something which has to be invariant under the torus action, then most of what's interesting that's happening has to happen at the fixed points of your toric threefold, vertices. And then you have something sort of less interesting happening along the edges, because along edge, a torus fixed curve connecting two of the fixed points, because your torus is scaling things along it, you can't have anything interesting in it. You just, in this case, you have a choice of partition on each edge. This can be viewed as telling you precisely what the scheme theoretic support of your sheaf is. Has to correspond to some, along such an edge, has to correspond to some monomial ideal in C join xy, which means partition. So the edge data in your fixed points, just partition. The vertex data is more complicated. So in the case of Donaldson-Thomas theory, it's pretty clear that the vertex data has to mean some sort of three-dimensional box configuration, plane partition. For example, if you're doing Donaldson-Thomas theory of C cubed, then so you have ideal sheaf of C cubed, which has to be invariant under the torus action. That means that it's given by an ideal generated by monomials. So there you're getting a box configuration fairly clearly. Here you're getting a somewhat different sort of box configuration. So again, just as an example, if you have like x equals, say, P3, then the picture you look at then is you have 4 fixed points for your torus action and an edge connecting any two. And the fixed points in your moduli space Sable pairs will be determined by, for each edge, you pick a partition. For each vertex, you pick a box configuration. There's some relationship between the two. In the general case where you have 3 edges coming into a vertex, they all sort of interact in some way, and writing out the details of exactly what sort of box configuration you get there is a bit complicated. But a simpler example, which is a much better starting point for proving the entire toric setting, is consider a local curve. So let's say the simplest local curve, c squared cross p1. So here the picture is just we have 2 fixed points over 0 and infinity on p1, and we have a single fixed line between them, 0 section here. So then the associated data that we have here is we pick a partition of the edge. What is it a partition of? It's a partition of the degree which we fixed, which is given by this parameter beta, the curve class. So we partition mu of d, and then we have box configurations, say b0 and b infinity. Any partition of D. This is a partition along the edge. So it corresponds to your sheaf. F has some support. If you look at the scheme theoretic support, that had better be invariant under the action, and sort of the piece of it along the edges, forgetting about data at the 2 endpoints, that's just given by a single ideal of length d in C adjoin xy. Corresponds to partition. So the box configurations, I haven't described yet what I really mean by that. I will in a second. But the way to think about them is, so if we were doing Donaldson-Thomas theory, then the box configurations, what that would mean is you take an infinite cylinder above your partition mu of that shape, and then you stack boxes outside of it, some finite number of extra boxes outside of it. For the stable pairs theory, instead of stacking boxes sort of outside the cylinder against the side of it, you'll stack the boxes under the cylinder. So something I didn't mention earlier is that the way to think about the relationship between stable pairs and Donaldson-Thomas theory is that Donaldson-Thomas theory with ideal sheaves, you're allowing isolated points to run off and do things away from the curve itself. And whereas with stable pairs, all the action is confined to the curve. And that's sort of analogous to here I'm saying that the box configurations for Donaldson-Thomas theory, you can stack boxes as much as you want outside this cylinder, this mu cylinder. Whereas for stable pairs, things are confined to the right underneath the cylinder. It's a simpler situation. Okay, so to be more explicit about what I mean by these box configurations. So reviewing here, mu, so it's a partition. This means it corresponds to a subset of lattice points in a quadrant. And this box configuration, I'm going to describe it as a subset which lies between an infinite cylinder on one side and a somewhat larger infinite cylinder on the other side. So here, this is just for some sufficiently large L. In other words, be some subset of lattice points which contains this infinite cylinder going off one direction, and you're putting finitely many boxes underneath it. So you're still contained in some slightly larger cylinder, which goes in the negative direction a little bit more. And something I haven't written down here is that this box configuration should satisfy the same type of requirements that a normal plane partition does, in that you want the set of boxes to be closed and are moving in certain directions. So in this case, you want, so as subsets of the doubly infinite cylinder mu cross Z, B0, B infinity should be closed under increasing coordinates. So a convenient way to actually think about these, I would draw a picture, but it's really hard to draw this sort of picture, and I think this is actually a somewhat better way of thinking about it. So a normal plane partition looks like, can be thought of as we take some partition, then we draw numbers in it, like 4, 4, 3, 2, 1, 1, something like that, where these are the heights above each square. It's a three-dimensional partition. So this is a regular plane partition. What we have here is the same thing, except that we are interested in the heights we're going below the cylinder. So all our heights will be non-positive, and we still put some sort of decreasing condition on them. So might have like 0, 0, minus 1, minus 2, minus 3, minus 2. So I'm going into all these details about what these box configurations are because of how the localization argument works. These are sort of the fundamental pieces that you get when you're working with these toric varieties. All right, so then when you actually do localization, to write things as a sum over the fixed loci, I'm still thinking about this case here with x equals C2 cross P1. So we just have two vertices and single edge. This will look like, well, first we take a sum choosing the edge partition, sum over partitions mu of D. And then we have a sum over box configurations B0 under mu of something, say more about what that is in a second, times an edge term, which is something that just depends on mu and is fairly simple. It basically is just the dimension of the corresponding irreducible representation of SD with a few other factors added. And then we have another term for the other vertex. So that's a sort of expression that one has to analyze to when one computes these toric stable pairs invariants. So, like I said, the edge term here is simple. Basically, what's going on here is that think about this in general as you're summing over finite number of choice for partitions, and then you have various factors which are each summing over box configurations at a single vertex. So what is this term here? Well, this is actually called the one-leg equivariant descendant vertex. I didn't write the descendants in here, but the descendants will just affect what these factors are here, which I didn't write down. That's where the descendants appear. They'll just depend on the box configuration. So if we rewrite this as just notation mainly, what we have here is a sum over the box configurations under a fixed partition mu of some weight, which will depend on the partition, on the descendant, and on the box configuration. So this is some rational function of S1, S2, S3, and then we have some Q dependence, though. Q dependence dependent on n, which, if you think about it, is basically counting the number of boxes. L of B is more or less just the number of boxes you're adding on addition to the cylinder you're stuck with over here. And this weight function here is, well, I'm not going to write out exactly what it is, but it is a function of so you're getting a rational function of the equivariant parameters, and it's a simple, in some sense it's simple, algebraically simple. You're doing some fairly straightforward algebraic operations. Function of the characteristic series of B. So, right, FB to be sum over points A1, A2, A3, boxes inner box configuration of T1 to the A1, T2 to the B, A2, T3 to the A3. This is some Laurent series in A1, in T1, T2, T3. Basically what's going on here with this weight is you're taking this expression, you're maybe applying the automorphism on rational functions. It replaces each t by t inverse, multiplying it by that, doing a couple other simple things, and then taking the Euler class of that, where you interpret like the Euler class of t to be S. Some simple algebraic procedure of getting from here to a rational function in S's. All right, so all of this was just sort of setting things up with the localization. So these t parameters are like, they're the parameters on the torus, as opposed to the s's, which are the corresponding equivariant cohomology classes. I mean, in this setting, they're just formal variables used for this characteristic series. All right, so the main step in the theorem for rationality for toric threefolds is that if we take this one-leg equivariant descendant vertex, and then we try to make the evaluation S3 equals S1 plus S2 divided by A. Then this is well defined and is a Laurent polynomial in Q. Its coefficients, which are rational functions in S1, S2. We've gotten rid of S3 by substitution. So I haven't said what A is here. And this should be true for any natural number A. So I'm not going to say very much about the details of how one gets from this main step to the full theorem. The basic idea is that, so this theorem is saying you have a polynomial, in fact, in particular you have a rational function on lots of different specializations of this S3 variable. And with a little care, you can interpolate between them to get a rationality result for one-leg toric invariance. One leg here is again referring to the fact that the vertices in question all have exactly one edge coming out of them. So by interpolation with this, one can get the one-leg case. Then one has to do other work to get from the one-leg case to the two-leg case into the full three-leg case, which you need for general things like P3. This is sort of the start of all of it, this substitution statement. The reason why you're considering this, substitution is that, so something I haven't mentioned here is that when proving the sort of thing, you actually want to work with relative theories usually. One way of thinking about why the relative theories are easier to work with, I mean, you can use all sorts of degeneration arguments. That's one thing, but also in this simplest case, I could write down C2 cross P1. I had two vertices. It would be better only of one vertex. If I took C2 cross P1 relative to the fiber over infinity on P1, that's the cap, then I have just one vertex, and I have some stuff happening involving the quantum cohomology of Hilbert's scheme of d points on P2 on the d points on C2 on the other side. And that quantum cohomology was already known to behave very nicely with respect to this substitution. This is something that follows fairly easily from looking at invariance on a twisted tube, where you take a local curve which is a total space of like O plus O minus O of minus A. And anyway, so that's why these substitutions are sort of expected to be nice. In terms of the actual statement of this theorem, being well-defined here refers to the fact that, so this vertex was defined as a big infinite sum over lots of box configurations of rational functions. And if you look at the terms individually here, they have poles of arbitrarily high order along this. the individual terms.
So I thought your L is always positive and LB isn't that always positive? Q?
Sorry, it's a different L here.
Oh.
This is L of B as in the length of B. That was just some parameter used to in the definition there. Sorry for the confusion. So this well-definedness part is really a statement about the massive pole cancellation has to happen somewhere. Because the individual terms have poles of very high order along this. So much of the theorem is showing this well-defined, and a little bit more work to show that you actually get a polynomial at the end. So again, really a pole cancellation result. So an example of how this works, the very simplest example you can write down is when you have no descendant and when you're in degree 1, your partition is just 1. So this can be computed quite easily. Turns out to be 1 plus q to the power s1 plus s2 divided by s3. So when we make, this is some complicated function which is definitely not rational. When we do the substitution, we're left with just 1 plus q to the a. In general, if we replace 1 by some other function, you're getting, in general, I think you get some sort of hypergeometric series, but not anything that's very nice to work with that way, since these box configurations, the various inequalities you have between heights of boxes really cause a lot of trouble. These are basically hypergeometric functions that have some magical cancellation happening when you make the substitution. Okay, so I'll say a bit about the strategy of the proof of this theorem, which is the strategy, the approach that we used here could also be used in similar other situations. For example, I'll say a bit at the end about how all of this changes when you try to work with Donaldson-Thomas theory instead of stable pairs, since you still have notion of one-leg equivariant descendant vertex, and everything looks very much the same, except that your box configurations are a bit different. Actually. So the first step is that, as I was saying, there's some pole cancellation that you have to discover there for the substitution to be well defined at all. And there's a way of making how this pole cancellation works. There's a very detailed way of explaining how the pole cancellation works, which is that you can, so your big sum is a sum over box configurations B under your partition mu. So partition this into finite sets, infinitely many finite sets. Since that's an infinite set. And so these finite sets, which we call SF, these are, SF consists of the box configurations B such that So FB, again, was this Laurent series in the T's, which is the sort of characteristic series of your box configuration. It itself is a Laurent series, but because it only extends infinitely sort of in very regular behavior up along this infinite cylinder, if you multiply by 1 minus T3, you get some polynomial. And then you do this substitution on T's, which is the analogous one to the ones on the S's. So you want to look at all box configurations which are basically the same up to doing this substitution. F here is some Laurent polynomial in T1 to the 1 over A and T2 to the 1 over A. So this is a finite set. And the nice property about these finite sets is that all the pole cancellation happens within these finite sets. So if we just sum over the box configurations in one such set, we again have this weight function. In the actual formula for the descendant series, we also had some Q factor here dealing with the number of boxes. But everything in this set will have the same number of boxes, so I'm not forgetting about the Q's. So if we just take this finite sum here and evaluate S3, S1 plus S2 over A, then on this finite sum it will be well defined. Moreover, so we need a bit more than that. This is enough to say that the overall substitution is well defined. We also need that it's a polynomial. And moreover, this is 0 for all but finitely many F. So these two facts together imply the theorem. So this grouping of the box configurations sort of completely addresses the question of where the pole cancellation is coming from. It's coming from inside these sets. The details of how this pole cancellation works are somewhat involved. Basically, they make use of certain properties of the ring given by taking n variables and pushing out by the ideal generated by the symmetric functions with no constant term. These are the elementary symmetric functions in x1 through xn. I mean, this ring has been studied in a lot of other contexts, but in the course of trying to prove this result, needed to find a few more features of this ring, doing algebra in that ring. So that's where well-definedness comes from. And this fact at the end that we need that the contribution from each SF is 0 for all but finitely many F, that comes from some refinement of the above version. It says that for all but finitely many box configurations, you actually get a little bit more from that argument than you needed. You get the cancellation of one more term in the Laurent series expansion of this about that. So this is a refinement of the methods used here.
So, and that only happens when you specialize this variable.
Yeah, so as I said in the example before, before you specialize, the vertex is some really irrational thing. After we specialize, we're getting a Laurent polynomial. I should say that, so A is any positive integer. And if you make A larger, then what changes here is that you have, as A gets larger, you'll have more and more f, always still find number of f, such that this is not 0. All right, so I'll just say a bit now about what happens when you try to apply the exact same method used here to try to study the dt vertex. So if you know a little bit about the descendant theory of, for dt, then you know that something has to go wrong, because in dt things are, you don't expect rationality. You get some ugly irrationalities, maybe not so ugly. They aren't very well understood yet. Well, it turns out that the whole argument works except for this step here. That is, you can still show by this method that the substitution is well defined. You get the pole cancellation you need for that. However, at the end of the day, after doing all the substitution, you're left still with infinitely many terms. So you've no rationality argument. That doesn't mean this is useless, I think. And this is something that I've been working on trying to exploit. Since what we get from this is still some massive cancellation. You have infinitely many f such that things don't go away in the substitution, but they'll be fairly well behaved f. So the box configurations that aren't cancelled away by the substitution they're the ones with, this is an approximate statement. The actual details of this are a little bit ugly, at least with the best bounds I have at the moment, but they're the box configurations with no gaps of size greater than 2a. So by this I mean that if you take two adjacent columns, then the heights of the corresponding box configurations shouldn't differ by more than 2a. In other words, the only box configurations that are left are sort of the smooth ones. And as A gets larger, they're allowed to be more and more, they're allowed to be less and less smooth. And in Donaldson-Thomas case, you're putting boxes outside the partition. You have lots of space to make arbitrarily large smooth partitions, smooth plane partitions. Whereas in stable pairs, because you're confining everything to this single cylinder, it turns out you only have finitely many options which are smooth in this sense. So, although the method does not prove something that isn't true, I mean, it's not, the DT vertices aren't rational, I'm hopeful at the moment that this approach might be useful in studying the irrationalities that appear in the DT descendant vertex. No, this is not the reduced DT. I mean, that's also a reason.
Yeah, but if you not reduce, then you already have this sort of series.
Right, so I mean, there's really no hope for it being rational. Yeah, I mean, DT setting is something sort of completely different because it's not rational. Like, it's not so nice. But this gives some handle on simplifying it by changing a sum over arbitrary box configurations to a sum over just the smooth ones. Okay. That's
So with the descendant, do you have a sort of conjectural statement between either your stable pair with Gromov-Witten or DT with Gromov-Witten?
right. So, yeah. So for a stable pairs Gromov-Witten correspondence, that's something that Rahul and I have been looking at more recently, trying to get that to work. And I'd say there's hope there, but we don't have any nice way of we don't have any actual concrete description of a correspondence. We have sort of the framework for one. And this rationality result for a toric case with descendant is useful for that because, so when you're doing the stable pairs to Gromov-Witten correspondence, you have to do this change of variables, replacing the q here by like e to the z, e to the z or iz, or depending how you're normalizing things. And that's something that you can do in this direction once we know rationality. You're just plugging, replacing q by a e to the iz in a rational function. And that makes things a lot easier to work with formulating conjecture that we know this side is rational, and so that gives us the opportunity of trying to write down explicitly what the Gromov-Witten side should be. It's so complicated because the descendants make all these correspondences more complicated.
Once you sum over, this will mean that, for toric, for example, the journey function will be rational?
Yeah, I mean, so there's a lot of work involved there.
So you described one piece, right? So
yeah, I described one piece, which was proving sort of this actually polynomiality statement for the vertex alone after the substitution.
Yes.
So the way the progression works is that you then use that by interpolating. You interpolate between lots of different values of A to get to prove it for one leg. threefolds. Actually, you start out by proving for the cap. Then you build all one-leg threefolds. So, like local pairs. Then you need to use some other methods, basically considering the correct threefold geometries to get relations to deduce the like the two-leg rationality statement from the one-leg statement, and then the three-leg statement from the two-leg statement.
I see. So still a lot of work.
Yeah, this is where all the computation is.
Yeah.
What's interesting is that the later steps of the procedure, going from one leg to two leg to three leg, that's stuff that doesn't use any special features of stable pairs. It works equally well for DT or for Gromov-Witten.
I see.
That's sort of purely formal ways of extending from one leg to three leg in any toric curve counting moduli picture. This is the one place where you actually have to work with the details.
Yeah, so I mean, is that